Hello, everyone. My name is David Murakami, and I am a researcher at NASA Ames Research Center. So the title of this talk is a little bit of a handful, sure, but what I want to discuss is the architecture for space traffic management that we've developed at Ames. So Ames has a long history working with the FAA for air traffic management, and more recently with drone traffic management, which is being done in a very different manner. So we've learned a lot in the process of developing that system, and it's a very different domain from space traffic management. But I think there are some common data exchange sort of problems, and I think there's a lot of overlap. So in this presentation, we'll begin with a little bit of background and motivation to describe the problem that we're trying to address. Then we'll go into the architecture that we've developed, some of the prototyping work that we've done, and I think also very important, describe what the long-term vision of this architecture could look like, what its benefits are for the space traffic management community. So, as we're all probably aware, a lot is happening in space. It's getting pretty interesting, and that might be a bit of an understatement, right? That might be like saying 2020 is turning out to be an interesting year. On the left of this slide, we have a couple SSA providers. So Exo Analytic Solutions here has been around for a while, and they've got a worldwide network of telescopes looking at GEO, and it's to the point where if a GEO bird explodes, you might be seeing a YouTube video of it up pretty quickly. Leo Labs has grown a lot over the past few years. They now have 3 stations, and they're working on developing a 4th. They're also focusing on services too, so not just providing orbit data, but also providing conjunction assessment services and that kind of a thing as a subscription to their customers. Underneath that, we have the space fence that's coming up and is going to increase the size of the catalog by a factor of 5. So that's is going to increase the number of conjunction warnings that come out. Hopefully they're all false alarms. I have EOS here listed because they have an interesting product that they're working on. They're hooking up a high-power laser to a telescope, and they're going to use radiation pressure to nudge space debris objects just a little bit to alter their orbit. That's a pretty interesting capability, but you can imagine that there's a need for coordination with something like that. CubeSats, academic CubeSats, as always, are a growing population, and there is a service called SatNogs, an open source ground station network, which I think is pretty interesting. So they're often the first ones to make contact with these CubeSats after deployment. And of course, there are the mega constellations, right? So Starlink is building over 100 satellites every month. They're launching every couple weeks or every month, something like that. Amazon has announced that they're really serious about their version of it, and that is going to lead to a lot more satellites. So there's a lot going on here, and to me that looks like a rapid increase in the diversity and quantity of the data sources and sinks, all of which need to coordinate in a space traffic management environment. So how do you get communication between all of these data sources and sinks? How do you get them to coordinate with each other? So for small problems, you can imagine point-to-point ad hoc connections being sufficient, but at some point, as the problem gets bigger, it's not. And I think we're well past that point. You need some kind of structure. So the one that makes the most obvious sense is a centralized system. So there you have all of your data sources. They feed information to this central authority, who does processing and generates derived products that go on to the data sinks. But there's the question of who owns it, who pays for it, who maintains it, and who determines the priorities of that authority. Also, this is a lot of work for that central authority too. Another way of approaching it, and the one that we're looking at, is a federated system. So you look at what that authority has to do, and figure out how you can split up those functions and devolve that work and bring those responsibilities down to the lowest practical levels. So this is less intuitive, and you have to be more careful when you develop something like this to ensure safety and that kind of thing. But it's not as heavy a lift. It's not as expensive to run as a centralized system. So there are some examples of this in miniature, like the Space Data Association. It sort of performs STM functions for a smaller group, for commercial satellite operators. Another way of looking at this that I think is appropriate is controlled flight rules versus visual flight rules. So in airspace, if you're in controlled airspace, you talk to an air traffic controller and they tell you exactly what altitude, what heading, what speed to fly at, because they have the big picture, they have all the information, the weather, where everybody is, that kind of thing. But under visual flight rules, there is no air traffic controller. Instead, the decisions are made by the pilot, and that's possible because they have sufficient situational awareness to be able to make those decisions themselves and be able to fly safely. So without a real structure, everybody would have to create unique point-to-point connections with everyone else they have to interact with, and that just doesn't work. That scales as the number of participants squared. You need to be able to publish data just once. So in the federated architecture, you do this by having a single point of contact with the STM network, where all of your STM relevant information is accessible and available as the single point of truth. We call that the STM service supplier. So you don't exist as little bits and pieces of data spread out over a bunch of systems, like this group has your old email address, this other one has your latest planned maneuver, but another doesn't. Instead, they all point to this single interface for yourself in cyberspace, and that you have the responsibility for maintaining information there. You also have control over what sort of information to share with who. So that's an example of devolving decision-making over who to share data with to a lower level. So with power comes responsibility. So it's important to have an onboarding process that ensures compliance to standards and to define roles for the participants and make sure that they're capable of living up to them. So by breaking apart and defining interfaces in this way, you allow services to be created in between. It's kind of like the open source development attitude. So if you want a feature, you can go to the developers, say, I would like to have this. They will tell you, hey, that's a great idea. Build it yourself and you can push it and we'll incorporate it into the next release. So this architecture hopefully encourages development of services by third parties. So the process of federating the functions of an STM system and spreading those functions out among the participants led us to define this architecture. So at the bottom we have the owner-operators and their spacecraft, and they are represented in the STM system by their respective STM service suppliers. That is their interface to the rest of the STM network. We have the conjunction assessment suppliers, which do calculations that perform conjunction assessments. The SSA suppliers that maintain catalogs and do observations. And this supplemental data supplier, which is sort of a catch-all term for everything else, like space weather and atmosphere models. On the outside, we have the spaceflight information system, and that is the interface for regulatory authorities to peer into this STM network and also get information back out. We have external stakeholders here defined, and that would be members of the public, such as astronomers, that kind of thing, who have an interest, and the STM gateway, which is sort of the stripped down version, the lightweighted version of that central authority that we were talking about before. So this is a federated system, and by contrast, something like SpaceTrack is most of these roles all rolled into one entity. I would like to work through a collision avoidance example here to illustrate how this STM architecture might work. So we begin with an owner-operator with its spacecraft. That OO then establishes a contract with an existing STM service supplier, or if it's sophisticated enough, it can create its own. That step exposes that owner-operator to the wider STM network, and that S3 can then contact the STM gateway and register itself and say that, hey, this is where you need to go in order to communicate all matters related to this particular spacecraft. The STM service supplier can now set up regular conjunction screenings. So it gets into contact with a conjunction assessment supplier and provides information like self-reported ephemerides from the spacecraft or planned maneuvers, things like that. The conjunction assessment supplier takes that information along with information from SSA suppliers who maintain catalogs and atmospheric models and other things like that from supplemental data suppliers. And when a conjunction is found, it sends conjunction data messages back to the S3 for consideration. Now, in this example, a conjunction between two active satellites has been found. So the S3 of the primary gets in contact with the S3 of the secondary, and they work out the mitigation. It might be that the primary is maneuverable, the secondary is a CubeSat with no propulsion, so in that case it's pretty obvious who has to move. Or the secondary could be a Starlink satellite with xenon propulsion and a short lifetime. It might not be too averse to performing maneuvers. So that negotiation happens between the S3s. They work out a solution, and that solution gets communicated to the owner-operator for approval and to the conjunction assessment supplier for validation to make sure that would actually mitigate this conjunction. That information is also sent out of the STM network out to the regulatory agencies for visibility and is also made available to SSA suppliers. Once the owner-operator has completed a maneuver, it sends its updated ephemerides, or state vectors, back to its S3. And that S3 then communicates that information out again to the Spaceflight Information Management System, where it goes to regulatory authorities who have an interest in this, and again out to the SSA suppliers who can confirm that the maneuver occurred as expected. This collision avoidance scenario is the one that we've been looking at for the developments of the lab prototype of our STM ecosystem. So we've written implementations of the S3, of the conjunction assessment supplier, of the SSA supplier, and have them running on separate workstations and communicating with each other through RESTful API calls. At the top left is the web service that we made for owner-operators to be able to send screening requests. Also, we developed a automated maneuver advisor to generate maneuvers for active on-debris conjunctions. Now that's not so much for operational use, but it was more of a way to explore what it's like to create applications that run on top of this infrastructure. So the plan for continued development of this architecture is to proceed through successive technical capability levels, and on each iteration, adding in new functions and new user groups. So first, we would like to flesh this out with small satellites in mind, in particular academic CubeSats. That's kind of a underserved user group right now. Second, to incorporate RF interference, that kind of information. And third, to overall mature the concept. So there are issues here that we didn't talk about for the sake of time. For example, you have these separate SSAs with their own catalogs. What do you do with that? How do you fuse that information? Fourth, we want to extend this space traffic management system to interface with air traffic management. So that would let us address launch and re-entry and suborbital flights, the issues that are involved there. And also interface with groups like the Laser Clearinghouse. So the final goal that we want to have is something that's built not just to solve near-term problems, but is designed from the start to be robust and scalable and easily extensible to other applications that third parties may want to develop. And with that, I would like to wrap up and thank you all for your attention. My email address is on the screen. Please feel free to get in contact, and below is a reference to a white paper that we wrote with a lot more detail. Thank you.